Hi guys, so today we're looking at lesson 2.4, and last time I realized I'd actually accidentally put in the wrong title. I had scale factors for 2D objects, so I don't know why I had that in there. I think I must have copied it from from Math 20-1 by accident. So what we're actually looking at today is angle properties in polygons. So remember last time we looked at angle properties in triangles, and so now we're moving into polygons with some of the same ideas. So just a quick little refresher or reminder on the different justifications we've used so far. Remember, supplementary angles that add to 180, complementary we don't see as much, but we'll probably see them more now that we're looking at polygons. So those are angles that add to 90. We have alternate interior angles are going to be equal if these two lines are parallel, and same thing for alternate exterior. Okay. So those are basically angles that are on the opposite sides of the transversal. We also have corresponding angles, which are angles that are on the same side of the transversal, but then usually one is interior and one is exterior, unlike these ones, right? So this is an example where we have an exterior angle here and an interior angle here, because the angles cannot be adjacent in order to be corresponding. All right, let's see, what else do we have here? Opposite angles. So remember, if you have any kind of like an X type shape, so two lines intersecting, then the angles that are opposite each other will be equal. And then the additional information we did last class was where we looked at information for triangles. So remember, if you add all three angles together in a triangle, they add up to 180 degrees. And the other thing that we looked at was the two non-adjacent interior angles for triangles. And the basic rule with that is if you have a situation where you have a triangle with kind of like an extended line like this, then basically the two non-adjacent angles are the angles that are not connected to an outside angle. So like right here, we have an exterior angle for the triangle. And basically what happens is these two angles here, so angle B and angle C, are not adjacent to that, so they're not next to it. And so basically if we add these two angles together, their sum should be equal to the measurement of angle A. Okay, so that's where we kind of left off last time. And now we're going to move a little bit further with that. Okay, so our first example today is a little bit of review, but also kind of some new information. Again, this should be information that you've learned before. So if you can recall from previous, learning what an isosceles triangle is. So remember that when you see two lines like this that are identical in a triangle, it means that the sides are equal. And when you have a triangle that has two equal sides, we call it an isosceles, so two sides of the triangle are the same. When those two sides are the same, that means that the angles that are formed by those two sides with like the bottom of the triangle, those are also going to be equal. Okay, so that's some information we can use going into this example. So it says if angle Q is known, so if we were to know angle Q, write an expression for the measure of one of the other two angles. So whenever we're asked in math to write an expression, that means they know that we're not going to have any number values because we weren't given any measurements here, but we want to write an algebraic expression that could be used to calculate the measurements of the other two sides. So using the information that we know from last time, we just finished talking about the fact that all the angles in a triangle are going to add up to 180 degrees. Okay, so we can say 180 degrees is going to be equal to, now what I kind of want to do is, remember we just said that these two angles are equal. So what we can do, instead of calling them angle R and angle S, which in algebra would imply that they are different, we want to give them the same variable. So we're going to call them both angle X because they are equal to each other. Okay, so 180 degrees is going to be equal to angle Q plus angle X. Oh, whoops, sorry, I forgot to put the angle sign in there. Okay, so it's going to be equal to angle Q plus angle X plus angle X. Now, we know that in algebra, if you have two things that are the same and you add them together, we can simplify that. So let's do that in the next step. So let's go 180 degrees is equal to angle Q plus, let's make this easy. I'm just going to eliminate the angle sign for these. So 2x. Okay. Now, if we want to be able to write an expression for the measure of one of these angles, that means we need to isolate x. So if we have q being added to 2x, then we need to subtract it from 180 to move it to the other side. So now we can say 180 degrees minus angle q is going to be equal to 2x. Now, because we want it to be an expression only for one of the x's, we need to divide out this 2 because it's being multiplied. So our final expression would be x is equal to 180 degrees minus angle q. And then we want to, actually I'm just going to use my ruler so that it's tidy, divided by 2. And that would be our formula that basically anybody now could go in and use if they knew angle Q. So if angle Q was, say, 110 degrees, you'd have 180 minus 110, which would give you 70 divided by 2, which would mean that each of these angles here would be 35. And then the math of that would make sense because 35 times 2 is 70, plus 110 gives us 180, and so we can see that those would add back up properly. Okay? All right, another piece of homework review. So this was a question that was in the previous section there, if you did your homework. We have a triangle here, but the triangle has a line through the middle of it, and they're asking us to prove that SY is parallel to AD. So basically that this line is parallel to this line. Now, sometimes when I'm solving problems like this, I kind of like to start at the end, which is basically knowing that my final statement needs to be that SY is parallel to AD. So you might notice that I've added in some lines here because even though we have a triangle here, we really do have, if we're trying to prove that these two lines are parallel, we kind of have this set up like we've been looking at in the past where we have parallel lines, or we're hoping they're parallel, and then we have a transversal running through. And that's a little bit easier to see if you extend these lines, right? So that you have, let's see, we're going to assume that we can prove this. So these two lines are our parallel lines, and then we have the transversal running through. And sometimes if you extend these lines, it can kind of help you to see those relationships that you've been working with already. So if I look over here, for example, I can see if these are my two parallel lines, I have a transversal. I know this angle here, 127. So what I could think of is, well, if this angle here was 127, then those would be corresponding angles, and then these lines would probably be parallel. However, because I've kind of like arbitrarily added in these lines, we don't want to use an exterior angle as part of our measurement. So alternatively, what we could do is, if we think about the fact that we have 127 here, if we go all the way around to the other side of the line, which would include this angle here, then that is going to be what value? Well, it's going to be a supplementary angle that should add up to 180. And so using this measurement, I can calculate the amount here. And if I calculate that amount, then I can use this angle as my corresponding angle. And now both of the angles that I'm looking at are inside the triangle. So I'm not including any things that have these lines that I've kind of drawn in. So I can use those two as a proof. So first of all, I need to figure out, is there going to be a way for me to find out if these angles are equal? Well, we already said we can figure out this angle here because of the supplementary component, but can we solve for this angle? Well, we already have this angle and this angle. So if we think about this shape as the bigger triangle, we know that these two angles plus this angle have to equal 180. So then I can solve for that angle as well. And then if those two angles are equal, then I can say that these two lines are parallel. Okay, so let's start out with maybe this one here. So angle NAD, which is this one here, angle NAD AD is equal to 180 degrees minus 127 degrees, which is 53 degrees. Okay, and so we can say angle NAD is equal to 53 degrees. And the justification for that is that we had supplementary angles. Okay, now the other measurement that we wanted was this NSY. Okay, so we can say angle NSY is going to be equal to, now remember this is looking at the sum of the triangles, so it's going to be 180 degrees for all three angles, minus the two ones that we already know, 98 degrees and 29 degrees. And so that's going to be angle NSY is also 53 degrees. And our justification for that is angles in triangle equal 180 degrees. Okay, so now my last statement should include what they're asking us to prove, which is that SY is parallel to AD. And so we can say that because of these two angles being equal, they're both 53 degrees. So we can say corresponding angles are equal. Okay. All right, so let's move on to another question here. This is a little bit more homework review, looking at polygons. So in this first one, this is kind of like a combination. So just to be clear, the reason why I'm doing this homework review is because we're using triangles, so this one for sure, but we're starting to move into, for example, in this case, we have triangular shapes, and we also have just kind of the older angle properties that we were using, but now we're starting to see them kind of forming into solid shapes, which are polygons. So we're kind of branching between, or bridging, there we go, between the previous understandings and the new stuff that we'll be working with, which is polygons. So in this question, it asked you to prove that quadrilateral MATH is a parallelogram. And all that means is, with a parallelogram, that these two sides are parallel and those two sides are parallel, but they're not at 90-degree angles the way a square would be. So again, if I kind of want to think backwards a little bit, basically what I'm trying to prove is that this line is parallel and that this line is parallel. So, and I'm given a bunch of different angles. Now I can already see that these two angles are the same, right? 45 and 45. So I want to think about what are those angles in relation to the justifications that we use. Well, if we think of this line here, MT, as a transversal, then the parallel lines it's cutting through would be, let's see, how would that be? That'd be HT and MA, right? Because this is an angle being formed with a transversal and this line, and this is an angle being formed with a transversal and this line. So essentially, by looking at these two angles being equal, we can see that MA is parallel to HT. Okay, so let's go ahead with our justification, which is angle excuse me, guys, angle MTH is equal to angle TMA, or actually, sorry, usually we go up in alphabetical, so AMT. Okay, and we know that if those those two angles are equal, then line MA is parallel to line HT. And the justification for that is, what types of angles are these? Well, we have 45 here, 45 there. They're on opposite sides of the transversal, and they're inside of these two parallel lines. So we have alternate interior angles. Alternate interior. Okay. Actually, because we're trying to prove angles are equal. Okay, so we see that those angles are equal. Now the other thing we could look at is, here we have a 65-degree angle. Let's see, so we have a 65-degree angle here. So if we could prove that this one was also 65, now we're looking at, you can always rotate this to think about it in a bit of a different way, because this 65, if this is our transversal still, is forming an angle between the transversal and line AT, and then this angle here would be forming an angle with MH and the transversal. So if we could prove that 65 and 65 are equal here, then we could prove that lines MH and AT are parallel, and then that would solve the whole entire parallelogram, because we've already proven that those two are parallel. So how can we prove that this angle here is 65? Well, if we break it down into a simpler shape, we have a triangle here. We're given two other angles. So if we can solve for this one, then we can make our proof. So let's do 180 degrees, which is the sum of the angles in the triangle, minus 70 degrees that we have there, minus 45 degrees that we have there. And when we do the math for that, we end up with 65 degrees, which is what we were hoping for. So we can say angle HMT is equal to 65 degrees. And our justification for that was angles in triangle equal 180 degrees. And then all we need to do is the same thing that we did up here, which is to state that these two angles are equal. So angle HMT is equal to angle ATM. And for those reasons, we can say that line MH is parallel to line AT. Line MH is parallel to line AT, and the justification is the same as here. Alternate interior angles are equal. Alternate interior angles are equal. Okay, so we've given our proof that both of those lines are parallel, which means that it's a parallelogram. Okay, let's introduce some new information. So looking at different types of polygons. So the main one we'll be looking at in this section here is a convex polygon. And with a convex polygon, basically what happens is each interior angle measures less than 180 degrees. So if you measure each one of the angles on the inside of the polygon, they're going to be less than 180 degrees. The total measure of the interior angles can be expressed using some algebra. So we would say the sum of n, representing however many sides that we have. So the number of those angles would be equal to 180 degrees times by n, which is the number of sides, minus 2. Okay, so for example, in this polygon, how many sides do we have? 1, 2, 3, 4, 5. And so our math expression to solve for how much each of these angles is would be 180 times by 5 minus 2. So basically 180 times by 3, and that would give us a total of 540 is going to be the sum of all of these angles if we add them together. Now, another thing that I didn't mention here, but I'll show you guys in a little bit here, is the word regular polygon. So if you have a regular polygon, it means that all of the angles are going to be equal. So basically what that tells you is that if you have a sum of 540 degrees with all the angles, you can determine how much each angle is by just dividing it by the number of angles, which would be 5 in here, and that will give you the measurement of each angle. Okay. So I've kind of gone through each of the different main types of polygons you guys would be using. You could get ones that are different, and in fact we'll do an example that has more than this, but this gives you the general idea of the most basic ones. So with a triangle, which we've already looked at, you have 3 sides. So the sum of your angle measures is going to be 180 times by 3 sides minus 2, which is 1, and so then the total sum is 180. If you have a quadrilateral, like a square, for example, something with 4 sides, it's going to be 180 times by 4 sides minus 2, so times by 2, which gives us 360. And you probably already know that because with a square, for example, you have 4 sides that are each 90 degrees, which adds up to 360. Okay, and then the rest are in there as well, so you can have a look at those. Now, the other thing I want to point out is the difference between a convex and a concave polygon. With a convex polygon, all of the interior angles have to be basically kind of like turned inwards. So convex angle versus concave here, right? So with this one, we have the angle directed in towards the center of the polygon. With a convex, they're all directed out from the center of the polygon. Oops, I'm flipping back to the beginning. Okay, so let's try some examples with this information. Just give me 1 sec here. So outdoor furniture and structures like gazebos sometimes use a regular hexagon. So there's that word regular hexagon, which basically just tells us that all the sides are going to be the same measurement and all the angles will be the same measurement. Okay, so determine the measure of each interior angle of a rectangular hexagon. Oh, I think that must have been a typo. That should be regular hexagon. I was going to say that doesn't make sense. So this one should be regular. There we go. So with a hexagon, another good thing to be aware of with that previous page that we were looking at is you should know these names. Okay, so you should know what each one of these represents. These are common prefixes that you'll see even if you take like chem and stuff like that. So tri means 3, quad means 4, pent means 5, hex means 6, hept means 7, and oct means 8. So you should have those memorized so that if you're asked like what would be the measurement of the angles in an octagon, you have to know that that means there's going to be 8 sides. So in this case, we're looking at a hexagon, which means that we have 6 sides that we're working with. Okay, and because it's regular, then we know that it's going to be equal sides. So we can use our formula, which is that the sum of our different sides is going to be equal to 180 degrees times by the number of sides, which in this case is 6, minus 2, and 2 is a constant, so we don't have to figure anything out there. So 180 degrees times by 4 is equal to 720 degrees total. So if you add all 6 angles, they're going to add to 720. Now they want to know what the measurement of each interior angle would be. So we want to say all of the angles inside of this shape are equal. So basically we can just divide this by the number of sides. So we can say 720 degrees divided by 6 sides, or more accurately 6 angles, is going to give us 120 degrees per angle as our final answer. Okay, let's try one more. Determine the measure of each interior angle of a regular, so remember that means equal, 15-sided polygon. So this is known as a pentadecagon. So basically what we want to do is the same thing. Our formula is Sn is equal to 180 degrees times by the number of sides, which was 15, minus 2. And that's going to be 180 degrees times by 13, which is going to be equal to 2,340 degrees total. Okay, now we want to know what each interior angle is, so we're going to do the same thing, 2,340 degrees divided by 15 sides. I was thinking about the subtraction there. 15 sides is going to be equal to 156 degrees per angle. Okay, so hopefully that seems pretty straightforward. It's basically just being familiar with the formula and working through that. Make sure that you're also checking to make sure, I'm not actually totally sure if that's on your formula sheet or not. If it is not on your formula sheet, be aware that you should have that memorized, okay? Because the only data you're allowed to use for tests is the data that's on the data sheet. So just a quick little recap here. The angles in polygons, the proofs that we have is the sum of the measures of the interior angles represented by this formula. If you want to determine the measure of each interior angle, you have to take that, basically the last part here where you calculate the total and divide it by the number of sides, which I kind of have been doing in 2 parts instead of combining it into one like that, but whichever way you do it is fine. And then the sum of the measures of the exterior angles of any convex polygon is 360 degrees. Okay, so you guys have a little assignment to do, page 99, a couple of questions there. And next time, what are we looking at next time? I believe it is... I don't know if I put that on here yet. 2.5. Let me have a quick look here. I believe it's kind of like a expansion on this one, but I don't have it memorized. Oh, exploring congruent triangles, right. So we're going to move away from polygons and kind of back to triangles. Looking at triangles that are congruent, so that means they have similarities. Okay, so I will see you then.